Right, I've got one more to let in. Right, I'm going to mute everybody, except that when you need to talk, Jamie, you talk. You unmute yourself.
Cool.
It's just the easiest way of making sure that nobody else is talking apart from those who need to be talking. Right, it's past, so I'll make a start. So welcome to tonight's Zoom lecture from the IAA. Our speaker tonight is Dr. Jamie Robinson. He's now at Edinburgh, having been at Queen's University for a while. He's had an extensive career, actually having done a physics master at Durham University, then coming to Queen's for a while, working on the origin and evolution of trans-Neptunian binaries, some postdoc work on asteroid science, also at Queen's, and he's now doing postdoc work at the University of Edinburgh on LSST software tools. He's an asteroid expert, and he's going to talk to us tonight about asteroids, the key to unlocking the secrets of the solar system. So I'll now hand over the floor to Dr. Jamie Robinson.
Great, thank you very much. I'll just start sharing my screen. Cool, so hopefully you can all see that title slide okay? Yes,
that's there, that's good.
Great. Well, thanks, Paul, and thanks for the invite, Terry. Yeah, I've been at Queen's for quite some time, and I actually do remember my sort of first year PhD duties helping out with the doors on some of the IAA lectures, so really honored to be invited to actually give a lecture this time, so thank you very much. But yeah, my career has sort of studied a whole variety of small bodies throughout the solar system, but today I'd really like to give you sort of like a whirlwind tour, an introduction into just sort of the world of asteroids, and give you an idea of what they are, how we study them, and how they affect us in terms of life on Earth, and teaching us about the history of the solar system. So our solar system as a whole consists of the central star, the sun, and the massive planets which orbit the sun in a rough disk. And then alongside the planets, we find the much smaller asteroids and comets. So in this artist's rendition figure here, we can sort of imagine ourselves situated on the edge of this disk, looking towards the sun in the middle. There's a giant planet there, and then there's this population of small solid bodies. These are the asteroids and the comets. So all these bodies, they were formed from the collapse of a massive cloud of gas and dust. And the asteroids are the leftovers of the growth of these solid bodies into the larger planets. So all these bodies in the solar system follow what is known as a Keplerian orbit around the sun. So in this little figure here, just sort of break down what that is for you guys. A Keplerian orbit is basically an elliptical path or trajectory with the sun at one of these two focal points. The important parameters that we use to describe the sort of shape and orientation of this orbit are the primarily the semi-major axis. So for a circular orbit, the semi-major axis would be the radial distance from the object to the sun. And this is typically measured in terms of astronomical units. So one astronomical unit is the distance between the Earth and the sun. Another important factor to describe this shape is the eccentricity. And basically the eccentricity describes how elongated this ellipse is. So an eccentricity of 0 is a perfectly circular orbit. And then as that eccentricity grows to 1, this ellipse becomes more stretched out and elongated. And then in addition to those two, we also have what's known as the inclination. And the inclination is sort of the three-dimensional tilt out of the plane that this orbit makes. So the vast majority, like the planets and most asteroids, are in the plane, but some of them do have significant tilts or even inclinations out. But we use these orbital elements to really describe the locations where we find all these different bodies. So for example, in this figure here, we're looking at a top-down view of the inner solar system. The terrestrial planets are these colored, the orbits of the terrestrial planets are these colored rings. And then we also have the planet of the orbit of the gas giant Jupiter in this orange ring. And what all these little dots are asteroids. This is the main asteroid belt, and it's found between the orbits of Mars and the orbits of Jupiter. So it's roughly spanning a distance of 2 to 3 astronomical units. And these asteroids are typically quite rocky in composition. And this is because they're so close to the sun that they can't really retain any like water, ice, or anything like that. But in contrast, whenever we zoom out and look at this, again, top-down view of the outer solar system, we now have the outer gas giants, so Jupiter, Saturn, Uranus, and Neptune in blue. And then beyond that, these dots are, again, asteroid or comet-like bodies. This time they're found in this outer Kuiper Belt. So the Kuiper Belt is predominantly found just beyond the orbit of Neptune, so distances greater than 30 astronomical units away from the sun. And these objects, they have a more sort of icy and volatile composition, especially when contrasted to the inner main belt asteroids. And this is because they're just so far away from the sun that they're able to retain hold of those more volatile materials. So these would be the two main sort of locations that we would find these asteroids and comets. But these small solar system bodies can also be sort of found throughout the solar system. They're always being scattered and interacting under the dynamical influence of the larger planets. And so that there's a lot of sort of movement between different populations, but then sometimes even these objects can undergo close encounters or collisions with the planets, including the Earth. So very interesting to know when that's going to happen. But in general, like the different compositions of these asteroids, what they're made of, tells us a lot about the materials that the planets formed from. And then all these different orbits that we find these small bodies on, this tells us a lot about how the dynamical structure of the solar system has evolved over time and how it's evolving now. So this makes overall the study of small solar system bodies like asteroids and comets an extremely important part for investigating the origin of the solar system, and to a certain extent us as well. So unlike the planets, asteroids are generally too small to be crushed into a more spherical shape under their own gravity. So instead, they typically have these more irregular potato-like shapes. And there is actual scientific literature referring to what is known as the potato radius, the size at which an asteroid stops being a potato. And then this gallery of images that I've gathered together on this slide here, these images are all thanks to dedicated space missions that we have sent out to fly by these objects really close distances and study them in situ. So some famous ones that I'm sure you'll have heard of are the European Space Agency Rosetta mission to Comet 67P Churyumov-Gerasimenko, and also the NASA New Horizons mission that went to the more distant Kuiper Belt object Arrokoth. So looking at this sort of rogues gallery, we see that asteroids display like a wide variety of shapes. So there's, for example, the rotating spinning top-like structure of asteroid Ryugu. Some objects are irregular or elongated, and then some even show these distinct lobes, sort of two separate bodies that at some point must have come together. And overall, this sort of, even though it's a small number of objects, it really shows that there's a really wide variety of physical processes affecting the surfaces of these small bodies. So, for example, the heating and sublimation of icy material, which drives this release of gas and dust, and that's how the activity of comets is driven. The rotation effects of fast spinning asteroids drives landslides of material down to form this equatorial bulge in this spinning top shape of asteroid Ryugu. And then we see on asteroids various like cratering effects from impacts, and even sort of micrometeorite impacts, and thermal processing is enough to like break down the larger boulders on these surfaces into this sort of finer, more powdery dust. So you can really see this on asteroid Itokawa, where there's like these two lobes with quite distinct boulders, but in between there's these sort of plains of very fine dust. But then I also want to like really emphasize that, you know, asteroids, as well as covering a variety of shapes, they also cover a vast range of sizes. So asteroids in general, you know, they can be anything from like micron-sized dust found in between the planets to dwarf planets that are like hundreds to nearly 1,000 kilometers in size. And this figure here really nicely highlights this like wide variety in the sizes. So this figure is, I believe, all the asteroids that were visited by a space mission, but this is only up until 2018, I think. But comparing this to the last image, so this here, this big lump is asteroid Letitia. This little tiny thing in contrast is comet 67P. So if I just go back a slide, you can really see how, like, you know, we're covering massively different size scales here. And this slide also sort of highlights that there's the asteroids follow what we call a power law distribution. And this means that there are significantly more small objects than big objects. So there's only a handful of asteroids in the solar system that are as large as like hundreds of kilometers in size, whereas there are millions and millions of objects that are less, a kilometer in size or less. So hopefully these two slides sort of give you an idea of like the variety of asteroids that we have in the solar system, and sort of hints at some of the properties that we're like interested in measuring. So that would namely be like what size they are, what shape they are, and what are they made of. So having shown these like really nice, perfect, detailed images of asteroids and comets taken from spacecraft missions, how do we actually learn about the vast bulk of asteroids, which we just can't all go and take images of with dedicated spacecraft missions? So the answer to that is photometry, which is measuring the brightness of asteroids from telescope images. So asteroids in general are so small and far away that they appear as like star-like dots of light on an image. And that's where the name asteroid comes from. Actually, it's Greek for star-like. But the main difference in an image between the asteroids and the fixed stars is that if you take multiple images spared out by time, that dot of light is going to move. So for example, in these astronomical images here of asteroid Florence, they've taken 7 different exposures and stacked them all on top of each other, each spaced by like a minute or so. And you can see this dot moving across the sky in this trajectory, whereas the background stars, they've remained fixed. But then the brightness of these asteroids, that's going to be determined primarily by their size and distance from the sun, or distance from the Earth, but also their surface reflectivity, the viewing conditions that you're seeing them under, and also the shape of that asteroid. So by observing an asteroid over like a sufficiently long time span and under varying viewing conditions, we can really learn a lot about their physical properties. So for example, in this figure on the right, I'm showing a sort of schematic of what's known as an asteroid light curve. So if you measure the brightness of an asteroid over time, if that asteroid is like a non-spherical shape, as it rotates around its axis, it will present different cross sections to the observer on Earth. So for example, in this first image of the asteroid, it's presenting its narrowest cross section. So that corresponds to a trough, a minimum in brightness, whereas up here it's presenting its full width. So that's a maximum brightness. And then from this, we can really we can tell how fast the asteroid is spinning. And if we get enough light curves, it's possible sometimes to reconstruct the actual shape of this asteroid. And like, to me, that's quite amazing, because you got to remember that these measurements are simply looking at a single unresolved dot of light and just measuring the brightness. So we can learn quite a lot just from photometry alone. But my sort of recent research into asteroids has focused particularly on the effects of how the viewing geometry, the viewing conditions, or what's known as the phase angle, affects asteroid observations. So excuse the crowded slide, please, but there's a lot of little things to show you here about what exactly a phase angle is. So the phase angle alpha is defined as the angle between the sun, the target asteroid, and the observer on Earth. And you can sort of imagine in this figure, as the Earth goes on its orbit around the sun, and the asteroid moves on its orbit around the sun, if we're like constantly looking at this asteroid, that angle alpha will change. And after we take into account effects such as like the distance of the asteroid, we'll note that as the phase angle changes, the brightness of the asteroid will also change. So at lower phase angles, as alpha goes towards 0 degrees and like the sun, Earth, and asteroid are perfectly aligned, the brightness of that asteroid will increase. And this is sort of, it's driven by sort of two effects. One of them is sort of like the fraction of the surface that's illuminated. So that's similar to the phases of the moon, as shown in this little figure down here. So whenever things are dead on, you know, the full surface is being shone back at us, we're seeing quite a large increase in light. But also the phase angle really depends on the surface properties of the asteroid. So that could be what the surface is made of, but also how rough it is. So is it like dusty or is it bouldery? You can sort of see that in this figure here, where it's like a lumpy surface will reflect different types, different amounts of light, like depending on the orientation. But how we utilize this for science is we use a phase curve model, like what is shown in this figure here, where the phase angle is on the x-axis and the brightness of the asteroid is on the y-axis. And basically, we'll take lots of observations over a range of viewing conditions and then try fit one of these curves to those observations. So one of the parameters of this function is this phase parameter known as g, and that effectively controls like the functional form, the steepness of this curve. And this is really valuable because essentially different types of asteroid surfaces will typically have different values of this phase parameter g. So this slide is showing some of my recent research where I have used these fitting various phase curve models to large numbers of asteroids so that we can compare the surface properties of asteroids in different dynamical populations, you know, from different locations in the solar system. And a really nice example of this is what are known as the asteroid families. So an asteroid family is formed through the catastrophic sort of disruption of a single parent body. So it undergoes a large enough collision that it's like fragmented into hundreds of pieces. And the result of this means that these pieces, they generally share very similar orbits. So in this figure here, I'm showing you some of those Keplerian orbital elements we talked about earlier. So there's the semi-major axis, and in this case, the inclination on the y-axis. And what this figure shows is all these gray background dots. They're just regular main belt asteroids. But what I've done is I've highlighted known asteroid family members, and they appear as distinct clusters within the asteroid belt. And then on top of that, I've done a phase curve fit similar to the one I showed you on the last slide for each of these asteroids. And then I've colored each of those asteroids by that phase parameter G. And the interesting thing is that because an asteroid family has like a common parent body, we expect all the family members to have very similar compositions, but then we expect different families to have different compositions to each other. So this is really nicely highlighted by the sort of different colors that you see emerging in these different groups. And just to really like drive that home, this figure here shows a histogram distribution of the phase parameter G, so the number of asteroids with a particular value of G. And I've looked at the asteroids from the Eos family and the Vesta family in particular. And you can see how this G allows you to really neatly distinguish between those two different families. So in this case, it's the Vesta family is what's known as, they're known as V-type asteroids. This is just like a taxonomic classification. But basically they have bright surfaces and a sort of basaltic composition, whereas the Eos family is what's known as K-type. They have silicate surfaces that are much darker. So you can see how we can really distinguish between these like different populations. And while I'm talking about my own research, I would like to just sort of touch on the subject of my PhD research, which was binary asteroids. So binary asteroids consist of two distinct bodies that are gravitationally bound to each other. So these bodies are orbiting each other around a common center of mass. You can see that quite nicely in this GIF of the Pluto-Charon system. There's a center of mass in there, and they're both orbiting it. But then that center of mass in turn orbits around the sun. And this is exactly analogous to like the moon orbiting the Earth. The only difference between the Earth-Moon system and these sort of binary asteroids is that the Earth-Moon system is just so much bigger, but also the sort of size ratios are quite different as well. But the cool thing about binary asteroids is that they can be found in like nearly all small body populations in the solar system, and they're detected through techniques such as direct imaging. So you can see here these astronomical images of various distant trans-Neptunian object binaries. You can see two distinct dots of light, and those will be orbiting each other over time. But you can also use sort of light curve techniques, like I mentioned a few slides previous, to detect signatures in that rotation period that are indicative of binaries. And the reason why I want to talk about these is because they're super important for investigating the properties of an asteroid population, because a binary asteroid, if you measure its orbital period, the orbital period of the moon around the primary, you can use Kepler's third law to obtain an accurate mass of the whole system. And this is important because it's one of the only ways to directly measure the mass of an asteroid body, other than like sending a dedicated space mission to fly by it. And then with that knowledge of the mass, and if we also know the size of an asteroid, you can then calculate a bulk density for the whole body. And from that bulk density, you can really estimate like the composition and internal structure. So you're learning quite a lot from asteroid binaries, and this single binary may represent the properties of the entire sort of dynamical population that the asteroid binary is embedded in. And then one of the other things that I looked at in my PhD is that you can really use binaries to test how models of how planetesimals formed, but also how they evolved in the early solar system. And like the fact that you have binaries today really sort of constrains the different types of perturbations, like encounters with the giant planets or collisions from other asteroids that they may have suffered up to the present day. But there'll be a bit more on that at the end of the presentation. So I want to get back to just how we observe asteroids in general. So in the past, pre-1980s, photographic plates were predominantly used in astronomy. So you would have identified asteroids as essentially a star that moves night by night. And typically, you'd have two photographic plates and you'd swap between them very quickly with an eyepiece, and you'd then find any dots that moved. So a really famous example of this is the discovery of the planet Pluto by Clyde Tombaugh in 1930. And I apologize for the size of everything, but you may see a white arrow pointing to a small dot of light that in one panel is then moved in the second panel. And from that, they were able to infer the presence of Pluto. But these days, we have access to high quality electronic detectors and high performance computers. So these two bits of technology are best utilized in what are known as wide field surveys, which are telescope surveys that scan through the whole sky that's visible to them. And essentially the way they work most of the time is after sufficient observations, they build up a good image of what is known as the static sky. So the static sky is stuff like stars and galaxies, things that are fixed in position on the sky and don't really change in brightness. So they have that static sky, and then whenever they take any new images, they can subtract the static sky image from the new image, and anything that remains in that image are what's known as transient sources. So these could be things that have changed in brightness. So for example, a fixed supernova explosion that suddenly lights up in a galaxy, or it could be a dot of light that is moved from frame to frame, and that's an asteroid. But this requires sophisticated automatic detection software to measure and link detections together. So the most advanced surveys have their own dedicated computational facilities. For example, this data server shown in this picture here. And it's also important to note that in wide field surveys, like individual objects are very rarely like directly targeted. This is what's known as sparse photometry. Things are just sort of imaged as and when they fall into the field of view of the survey's schedule. So the challenge these days is how to extract useful information from like these sort of irregularly spaced serendipitous observations. But a prime example of one of these surveys, which I actually work with, is the ATLAS survey. So ATLAS stands for the Asteroid Terrestrial Impact Last Alert System. And it's composed currently of 2 half-meter telescopes that are located in Hawaii, although the network of ATLAS telescopes is due to expand. So they're currently commissioning a telescope in South Africa and Chile. And basically the idea of these telescopes is that they operate as autonomously as possible. So the domes open on a schedule and the telescopes point and scan through set routines to cover the whole sky. So you can see here on the right here, this is a sky map showing how these orange boxes are the fields of view that the telescope is taking. So it scans through, covering as much of the visible sky to that telescope as possible, avoiding stuff like the bright near full moon. But as the name suggests, the primary goal of ATLAS is to spot potentially hazardous near-Earth objects that could be on a collision course with the Earth. But in the process of searching for these dangerous objects, it's covered a lot of the sky, and it's got hundreds of photometric measurements for hundreds of thousands of different asteroids. So as a member of the ATLAS collaboration, this gives me access to like massive amount of data that I can use to study the properties of asteroids. So for example, those phase curves of asteroid family members I showed you, that's all from ATLAS data. But as astronomers, we always want bigger and better telescopes, of course. So in 2023, the Legacy Survey of Space and Time, which will be located at the Vera C. Rubin Observatory, it's currently being built. In 2023, it will start. So here's a picture of the dome, the facility pretty much nearly complete from April 2021. I think they're still obviously putting the telescope and stuff in, but the building itself is built. ATLAS will start scanning the sky similar to ATLAS. Here's the sky map of the sort of one of the proposed observing strategies for LSST, where it will sort of scan through the southern sky, avoiding more the galactic plane, but also dipping into the northern sky to get the sort of ecliptic spur where there's a lot of asteroids extended up there. But the great thing about LSST is that it's a much bigger telescope. It'll be able to observe much fainter objects than ATLAS. And as a result, it will discover a huge number of new asteroids and going down into smaller sizes than we've ever been able to explore before. So this little table in the bottom right here just sort of gives you a sense of this scale. So we currently know 650,000 main belt asteroids. LSST alone is going to discover 6 million. And typically, most of those objects will have at least 200 photometric observations. So like this is going to be a game changer. It's going to be really great. And like I'm sort of involved in the development of ATLAS. Like at Edinburgh, my main postdoc task is to work on developing the software tools that we're going to need to deal with this huge amount of data. But like Queen's University is also really heavily involved. Lots of people are very interested in what LSST will do. And just to really drive it home, here are some numbers to give you a sense of the scale. So LSST is going to be an 8-meter telescope compared to the half-meter single ATLAS telescopes. The camera's going to have 3 billion pixels, and it's going to generate 30 terabytes of data in a single night. And then this slide that I've shamelessly stolen from Mario Juric, this highlights how LSST's software works to link together detections into moving objects and discover new moving objects, where basically the telescope will visit the same field 2 times in one night. So you get 2 detections of an object on night 1, and then sometimes more than 2 on night 2, more on night 3. It matches these pairs on a single night into tracklets, but then the software goes through and matches these tracklets into longer tracks. And it's these tracks that are then turned into new objects and added to the database. So like this sort of sounds simple enough, but just imagine doing this for millions of different detections in a single night for a time span of the 10 years that the survey is going to run for. So it's a huge task and like couldn't be done without modern computational facilities. But steering away from the observations now to like why we should actually be caring and concerned about asteroids. I've mentioned briefly that like surveys such as Atlas, they're designed to discover the possible dangerous asteroids out there. And asteroids are dangerous because sometimes they can impact the Earth and cause a lot of devastation. So why should we care about these impact events? Well, basically, we know that these extinction level events have occurred in the past. The most famous example being the extinction of the dinosaurs many millions of years ago. And from all of our observational surveys, we do know that there are asteroids out there that are evolving into the near-Earth space. And from near-Earth space, they can pass by the Earth quite closely and then eventually evolve onto an impacting trajectory. And although the extinction of the dinosaur was millions of years ago, we know that like it's inevitable that an impact will happen again. So this initially all sounds like very depressing. However, we're in this amazing like level of human civilization where we know enough about the danger, but we're starting to get a level of technology where we can actually like have a chance at mitigating these hazards, which is very cool. But just for a bit of context, I want to emphasize that there is like the things we should be worried about are the big events, the big impacts, but there is a constant flux of interplanetary material encountering the Earth all the time, and we are fine for most of it. So the vast majority of these objects hitting the Earth's atmosphere are so small that they burn up, and we see them as bright streaks of light, which are known as meteors. And this is essentially the kinetic energy of the object hitting the Earth's atmosphere and the friction with the atmosphere, releasing energy as heat and light, giving off a bright streak of light, like you can see in this figure here. Sometimes a small solid fragment, a meteor may be large enough that a fragment of it is able to survive that burn up and hit the ground as a very small meteorite. So a good example would be you might remember in the news hearing about the Winchcombe meteorite that landed in England in February of last year and is now in the Natural History Museum. But then we do get these more high energy events where like they're called fireballs or bolides. And they're essentially just a higher energy, brighter meteor event. And then this figure here is very interesting. It shows a map of the Earth. And then on top of that are all of the detections from US government sensors, presumably for monitoring nuclear weapons and stuff like that. But they're able to pick up these like flashes of energy in the atmosphere. And that's since 1988 up to the present day. And you can see that these impact fireballs are like spread completely over the globe. And they're color scaled by the energy released during that event. And basically I'm not going to explain the energy scale too much because I don't really understand it that much, but most of them are blue, which is fine. We see a flash of light and we're not affected by it. But as we get to larger objects impacting the atmosphere, we get to more and more energy. So thankfully there's much more blue things than there are yellow and red things. But whenever the red things do occur, we want to be concerned about this. So this big red circle here, you may recall hearing a few years ago of the Chelyabinsk event from 2013. So that's shown in this image here. Chelyabinsk was very famous because it occurred over the Russian city of Chelyabinsk in Russia. Russian city of Chelyabinsk. And it seems that Russians everywhere all have dash cams on their cars. So there was actually lots and lots of this footage similar to this dash cam here that was able to be used by scientists to reconstruct the trajectory and estimate the energy of this event. But for context, the Chelyabinsk event was caused by something that was about 20 meters in scale. But that 20-meter object burning up and exploding in the atmosphere released enough energy to blow out windows all across the city. I think like 1,400 people were injured as a result of the secondary effects of that blast, mainly caused by the glass. But we know that there's like as I mentioned before, there's far more smaller objects than bigger objects. So estimates of how often something like Chelyabinsk would occur is approximately once every 10 years. But then we start getting to like bigger objects and more devastating events. So looking further back, there's the Tunguska event from 1908. And this was a large explosion over Siberia that flattened like 2,000 kilometers squared of forest. And the best explanation for this is a airburst explosion similar to Chelyabinsk, but on a larger scale. So they estimate that the Tunguska event must have been about 40 meters in size. And then going further along this size scale, we start to get to the really devastating events. So, for example, the Chicxulub, the Chicxulub impact that formed a very large crater on the Yucatan Peninsula. This occurred around 66 million years ago and is believed to be responsible for the extinction of the dinosaurs. This is like a 10 to 15 kilometer sized object impacting us. But reassuringly, you can see that like as this size increases on this handy infographic, you see that the frequency of these events that we expect really increases. So like you don't expect a Chicxulub event to happen, very frequently at all. And another thing to be reassured about is down here in this figure, it shows because the largest objects are the brightest and the easiest to discover, these objects that we really need to worry about, we've found nearly all of them in the near Earth space. It's the ones that are smaller and less well known that we need to worry about, and they happen more frequently. But to reassure you, people do consider planetary defense, and there are some things that we can actually do to defend our planet. So, for example, various governments and government agencies are very interested in like preparing for these events, and they actually do perform sort of test exercises. So, for example, on the left-hand side here, they essentially invented a fake asteroid called 2021 PDC, and then sort of released observations of this asteroid in like a realistic manner to see how quickly the astronomy community could, work out its orbit and assess how dangerous it was and all that sort of stuff. So you can see up here, this is like a top-down view of the Earth's orbit and all the possible orbits that the astronomers are discovering from these asteroids. Eventually, the astronomers were able to narrow down a really precise trajectory and discover that the asteroid was going to impact somewhere in Central Europe, hypothetical asteroid, again, to emphasize. But at this stage in the exercise, they realize, they don't have the warning time to really do anything other than like measure the asteroid's trajectory and evacuate the areas that are affected. But now, like for a long time, people have thought of other ways of possibly dealing with these like impact events. So one of the options is deflection. So, for example, you can use a kinetic impactor to slam into an asteroid body and to try and knock it off course. Or there's what's known as a gravitational tractor. That's shown in this figure down here, where basically you send a spacecraft to go in a very specialized halo orbit of an asteroid. And if you have enough time to do this, it's actually quite efficient. The mass of the spacecraft pulls the asteroid off its collision course. And one thing people always talk about, and it's probably the most popular one in the mind of the public, is just destroy the asteroid, fire a big nuke at it or something. You know, stuff like movies like Armageddon get in people's minds. But actually, this is probably one of the worst things we can do, because if we recall back to this slide here, let's say, you know, there's a 1,000-kilometer asteroid coming straight for Earth. We could blow it up, but then we might be left with a whole swarm of 100-meter, even tens of meter size things. And each of these individual things can cause a massive amount of destruction by themselves. So destruction is generally a bad idea, in my opinion, but who knows, if we're like last minute, nothing else to do, maybe firing a nuke at it might, might work. But like I mentioned previously as well, that the stuff like the Atlas survey is looking out for these objects. This is how we're characterizing them. So as a member of the Atlas team, what I do is I actually scan through the data streams from the telescope. So being in the UK, we're actually in a really fortunate place where during our daytime, the Hawaiian telescopes are in their nighttime, and they're scanning through the sky, looking for these objects, and I can like look at that data coming in real time. So like this is a screenshot of the web interface that I'm presented with whenever I see a new object. And basically, it looks very complicated. It took me months to figure out what was going on here, but essentially I've got all these images of the asteroid. This should be a GIF that plays, but I couldn't get it to work in my PowerPoint, sorry. But basically I can see a dot of light moving across the sky. And then I can see all these other things like, oh, it's got a good asteroid-like motion fit. It's inbound to the Earth system and stuff like that. And what I'll do is I'll submit this object to the Minor Planet Center. And if the Minor Planet Center checks it and says like, oh yeah, this is definitely a real object, and oh, it's near the Earth, it goes onto a different website called the Near Earth Object Confirmation page. And once it's there, that's that object publicly advertised as something that other observers can go and follow up on and try to confirm the orbit of. So this object, for example, I spotted it on the 25th of November. And then after a day, it was designated as a real object, 2021 WR. And whenever the time to check the telescope comes, I have to do it no matter where I am. So I've managed to find out how best to get mobile phone signal to hotspot my laptop on like some nice isolated Scottish hikes. Secret is high ground, and hope for the best. But then, assuming we do find one of these dangerous asteroids, I mentioned that like the exercises have shown that we don't have the response yet. So this is now what agencies like NASA and ESA are testing. They're actually at the stage of trying to deflect an asteroid for the first time. So this is the subject of the NASA DART mission and the HERA ESA follow-up mission. And basically, DART is a kinetic impactor. It's targeting the Didymos asteroid system. And this is one of those binary asteroids we've been talking about, where the main body is Didymos. It has a small moon called Dimorphos. Although before this got an official designation, it was known as Didymoon, which I quite liked. But it's important to emphasize that this is purely like a test exercise. Neither of these objects are at risk of impacting the Earth. But the goal of the DART mission is to sort of test this kinetic impactor deflection strategy by slamming into Dimorphos. And basically, this is sort of shows what's going to happen and how we're going to assess its effectiveness. So DART was launched very recently, 24th of November, and it's planned to impact on the 22nd of September, 2022. I've heard that the best way to describe DART is that it's the size of a small horse. So they're firing this horse-sized object at the moon, and this is not going to unbind the moon from its orbit, but it will change the orbital period of Dimorphos around Didymos. And this then means that, you know, from the telescopes on the ground, you know, using that sort of light curve analysis, we can measure the change in period. And it will also be, the change in period will also be assessed by a CubeSat that accompanies DART called LichioCube. And then the actual crater formed by the impact event will be followed up a few years later by this separate European Space Agency HERA mission. So we're now reaching the end of my talk, and I just really like to sort of briefly tell you about, we talked about lots of different things, but I want to sort of leave you with like the big picture science that asteroids are teaching us, namely, how did the building blocks of the planets form, and how have the planets moved and changed since they formed early on. So just to sort of reiterate, like the solar system formed from a cloud of gas and dust, but those very tiny small particles of dust have to grow into giant planets. And typically the way that this occurs is as that cloud of gas and dust collapses, it forms a disk. And within that disk, little tiny particles of dust can, encounter at very low collisional speeds, and they grow and form these sort of like fluffy, fractal, but very fragile structures. And these are typically like referred to as pebbles, but like the meaning of the word pebble is very far removed from like a pebble you'd pick up in a river. But the problem is that these things are so fluffy and fragile that as they grow more massive, they start hitting these things known as growth barriers, where particles start to encounter each other, and rather than sticking together, they'll start to bounce apart and not gain any mass, or even worse, they'll hit each other and then fragment back down into their constituent dusty particles. So for a long time, this has been like a puzzling thing, like how can solids grow large enough to continue to grow into like asteroids, comets, and planets? And one of the sort of more recent ideas is that similar to how the main solar system collapses down, small dense fragments of gas and dust in this disk can collapse under their own gravity, and that contraction and containment allows them to like jump from these sort of pebble sized objects up to like 100-kilometer sized planetesimals. But one of the side effects of this way of forming planetesimals is that this gravitational collapse model means that most planetesimals, like in theory, should form as these binaries that I've been mentioning throughout the talk. And this is something that, I looked at in detail with my PhD. So this is a snapshot of various stages in one of these collapse simulations, where you start off with a spherical cloud of particles and it collapses under its own gravity and flings stuff out. But in the dense core, you get planetesimals growing very rapidly. And because these clouds are rotating, they tend to also form binary systems that rotate. But the sort of really neat thing about that is that in certain regions of the solar system, you do find these binaries that we think formed in the very first stages of the solar system. And these binaries that form, they may have, retained their binary orbit, so they may have contracted down into these bilobed contact binaries. So Arrokoth, the target of the New Horizons mission, is a really good example of this. But again, these binaries are really important for telling us about, how the planetesimals grew out of the dust and then went on to form the planets, but then also, the sort of like conditions that these planetesimals evolved in. So for example, we would have expected large collisions to disrupt these binaries, or dynamical interactions with the planets to like destroy them as well. So the fact that we see some of these binaries in populations today is like really valuable for constraining these models. And then also the sort of asteroids in general tell us a lot about planetary migration. So there's pretty much the general consensus is that the solar system initially formed in a much more compact configuration, with the planets growing rapidly of this like massive disk of planetesimals. So this figure on the left here sort of shows a schematic timeline of one of the leading theories of how the solar system formed. So we've got time increasing from the birth of the sun on downwards on the y-axis, and on the x-axis we have the radial distance of the various bodies and planets. So we can see at the early times, we have these sort of large planetesimals forming. The giant planets are located in this middle part of the disk. And then we have different populations of these small asteroids and comets. And the color indicates, these things are red, they form near the sun, they're probably rocky. These things are blue, they form far away, they're probably icy. But basically what happens is the planets take these, they interact with each other and undergo instabilities and move inwards and outwards on these migration paths. But in the process of moving inwards and outwards, they're flinging the small bodies around and mixing them together. So for example, we get here the main belt forming as a combination of material that formed near the main belt location today, but also outer belt material that was thrown inwards. And on top of that, we get a lot of stuff that's scattered outwards. And this stuff scattered outwards and pushed outwards by the migration of Neptune, for example. This then goes on to form the outer Kuiper Belt. And then furthermore, things that are thrown even further away, they form this massive spherical distribution of asteroid and comet-like bodies. And this is the hypothetical Oort cloud. And we think the Oort cloud exists because it's the source of comets falling in from all different directions towards the sun. And then, to bring it back to binaries just once more, the fact that we have certain populations where binaries survive and certain populations where they don't, this really constrains the amount that these planets have moved and the amount of dynamical excitation that these different populations have suffered at the hands of the giant planets. So I'll end here with my conclusions. Basically, the asteroids tell us how the planets formed and how the planets moved. We really need to understand the asteroids and the impact threat they pose for our continued survival. But there's deeper surveys occurring to find more of these objects and new asteroid deflection technologies that are being tested. So we're making great progress with planetary defense. So nothing to worry about too much, but please continue to give us funding. So. But happy to take questions on anything.
Okay, Jamie, thank you. That was absolutely excellent, of course. And it's a fascinating subject and really the one that's come on a lot in the last probably 40 years or so, isn't it? And particularly with, I worry a little bit about the impact threat aspects of it. And am I right in thinking, I think I read this somewhere, but you can probably tell me more about it, that it's still the case that in terms of impact threats, most of them have actually come past us before we see them. Is that right?
Yeah, so it's there's what's known as near Earth asteroids, and these are objects that have evolved from typically the main asteroid belt, and they've been sort of flung in under the influence of Jupiter to pass within Earth space. But that's saying even if that orbit is relatively near the Earth's orbit, it's probably we'd have to be in the same place at the same time, as well as sharing a similar orbital space. Yeah. So it is actually definitely the case that, a lot of these things, we're watching them and seeing, are their orbits changing? Are they evolving? So I think Apophis is a very good example of an object that we've known about for a long time, but people are concerned that have been concerned that its orbital evolution in the future could bring it onto a possible impact with Earth. But that's why people observe these things really detailed, and we can really constrain, will it just miss us? Will it hit us on the next pass? Stuff like that. But then we're talking about we got much longer time scales than something coming out of the blue.
Yeah. And the bigger ones we can see further away, hopefully. Is that the
Yeah, so just in for all asteroid populations, we have a much better level of completeness for the largest objects, and which is reassuring because the largest objects are going to be the most devastating ones. And then the smallest objects aren't really going to do too much damage, but it's those middling objects where we know about a lot of them, but there's still stuff out there and they can still do a bit of damage.